Hello guys, I actually did this video before, but I made some stupid errors. I did not even see it, so I have to do this. I'll do like 15-20 minutes, I'll be done. So, where do I start? Let's say we have a three-dimensional coordinate system, and in this 3D system, we have a section of a surface. We have a section of a surface that looks like this. It looks like this. And what I'm trying to do, this is going to have two parts. What I'm trying to do is I want to define a tangent plane, but I'm not going to do it in this video. I'm going to do it in the next video. A tangent plane is a tangent plane is when a plane is tangent to a point on the surface. But I'm not going to go into that now. I'm going to talk about the gradient and tangent vector. Let's say we use a plane to intersect this surface. You know, the surface is bent like this. So if you use like a plane to go through, it has like a contour mark on top of it. We have like a sketch and something that looks like this. Something like that. Because we don't have this sketch looks like an amoeba, so it's something like this. Something like that. So it's like a perforated top. So because we have no function to describe this kind of curve, what we do is we introduce a parameter called t. T ranges from anything. In this example, in this derivation, t is going to be the independent variable, x and y's, because this is a surface in 3 dimensions, so we can't use x and y to define it. X and y are going to be intermediate variables here. But let's say we do not know we're going to use a plane to intersect the surface. We're going to have f of x squared y is equal to z. That's a section of the surface. So it's given by x and y initially as the independent variables. I want to show you something called a level curve, because when a plane intersects this surface in 3 dimensions, we restrict the whole of the surface. We restrict everything, so we have a level curve. So let's say we have something called an ellipsoid. Basically, a sphere is under an ellipsoid. So let's say we have something like let's it in 3 dimensions. Something like that, it's an ellipsoid. So let's say it ranges from negative b, or the z-axis, to b. And we create a level curve. What a level curve does is that it restricts the whole surface, the whole 3D surface shape. So let's say we restrict it here. So what happens in this kind of picture, everything is restricted. So we have this function to be equal to a constant, not a variable. So you can see this is a level curve, so it stops here. So we're restricting the dependent variable axis. So that's what's going to happen here. So what we're going to do is we're going to project this sketch on the xy plane. Since we're doing that, so it's going to look something like this. So we have no function that it can describe this curve or this shape, whatever this is. So we introduce a parameter t. So we describe this curve, this shape, as a vector function given by x of t plus y of t. So therefore, at any point, if you want to find the tangent, the slope of the tangent line at any point is going to be r prime of t, or dr dt. Because they are vector functions, they have unit vector components. Now, okay, so because this is restricted as a level curve, this is the original function, but when it's restricted, when there's a level curve, it's f of xy equal to some constant c, and this is how it goes. X is x of t, is a function of time. Therefore, if we are interpreting this one, not this one, z is equal to, is the dependent variable, x and y, intermediate, they're not dependent. Oof, my head. Intermediate variables, and t is the independent. Sorry, I'm trying to do this fast because I already did this before and I forgot to do something. I mean, I made a mistake, sorry. Independent. And I'll tell you the mistake I made. That's defining what this is. This is for the level curve. The level curve gives you a contour map of a restricted surface in 3D. After this video, I'll make another video and I will describe what I'll be doing in that video is I'm going to try to describe a tangent plane. Here I'm only going to define a normal, and I will define, because these are only two variables, right? So in the next video, you'll see how I'll extend the concept, talk about 4 dimensions, 2 dimensions, and we'll talk about a tangent plane to a point on the surface. What else? So we already know what the rate of change of the vector functions with respect to time. It can be anything actually, it doesn't have to be time. But in this case, we're calling t time. With respect to time is equal to the horizontal component with respect to time and the vertical as well. So what am I doing? So we know f of x comma y is equal to some constant c. So if we take the first derivative, this goes to 0, because if you take the derivative of any constant, it goes to 0. But this is multivariable function calculus. We can't have we have to have partials now. So we have for this to be so, we have the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt equals 0. So this was where my mistake was. I made a mistake here. I was writing dy. In my brain, I was writing partial of y with partial of z with respect to x and so on and so forth. But I didn't know what I was actually writing was the partial of y with respect to t times dy dt and so on and so for x. So I was like, oh, how did I make this sort of mistake? So anyway, that's for that. So this is true, but I want to show you something interesting. If we had a vector called A that's given us, let's say, phi I plus let's say lambda j, and another vector B giving us ki plus lambda j. There are two ways of multiplying a vector. The first way is by the method of dot product. If you multiply two vectors by the method of dot product, we have a scalar function. But if you multiply two vectors by the method of cross product, we have a vector function. Because if you take two vectors, cross them together, you have an orthogonal vector. That's a vector that's literally orthogonal to the two vectors you crossed originally. But if you take two vectors and multiply them by the method of dot product, you have a scalar function. Therefore, if you do A dot B, you multiply this and this, so the I goes away. So you have equal to k phi plus lambda squared. Same thing here. You can take this as a vector I, and take this as an I, take this as a j, take this as a j. So we have f prime of x comma y equal to with the dot product. Sorry. So yeah, you can take these two as vectors, and what this is defined as, we define this as the gradient. Del, we call it del. Yeah. So del of f of xy multiplied by the method of dot product with, because we already defined what this is. This is exactly what I got here. So this is r prime of t from here equal to 0. And when the multiplication by dot product of two vectors equal to 0, that means, therefore, it's orthogonal to that's what that simply means. So that's pretty much everything I did before. What else do I need to say? What else do I need to say? I think that's about it. So, okay, we already know what this is. This is a tangent. This is a tangent. Okay, just stand up now. This is the tangent at any point of this vector function, this defined primary. this parametrically defined vector functions, I can't pronounce that. This is a tangent vector, right? So it gives you the tangent of the slope of the tangent at any point. Since this tangent is orthogonal or at 90 degrees or perpendicular to this vector, therefore, we define this to be the normal to the tangent at the same point. So, 3 things you should go back home with today. 3. Or if you're already at home, just take this to note. Thank you. This is just the beginning of what I actually want to show you. This is, now we've defined the normal, and when we want to define a plane, I'll talk about this in the next video, but anytime we want to define some plane, we need a normal to that plane to define it. And now, this will be the intro to the next video I'm going to do. Thank you very much. I made this silly mistake in my last video, so I'm like, damn. Okay, now I'll make the correction. Thank you very much.